here to the Pomona Valley Amateur Astronomy meeting here. I used to live up in Pasadena myself, and I'm familiar with the colleges out there like Harvey Mudd and Pomona College. So I actually thought I'd start by testing the Pomona Valley amateur astronomers to show them my second favorite pattern of stars in the sky. And I feel like you would catch me if I called this a constellation, because most of you, unlike most of the public, know that when you're not looking at a constellation here, you're actually looking at an asterism, because of course the Big Dipper is part of the constellation for people with very vivid imaginations of the Big Bear. So that's my second favorite pattern of stars in the sky. And to find my favorite, you have to look elsewhere. And not surprisingly, my favorite is this, and you are actually looking at a constellation here. It's known as Orion. And I maybe it's just because I've stared at it so much that even I can see a hunter in the pattern of stars here that is known as Orion. One of the very few constellations I actually can see the pattern in. And why do I love this constellation so much? Well, I love it because it's so prominent in the sky and I can always find it. And the other reason, of course, is that it harbors my absolute favorite star in the entire sky, and arguably the most famous star in the sky, if not in the at least in the top 5. And you probably all know which one it is in here. It's this big, bright red star in the shoulder of Orion the Hunter. And so why do we love this star so much? Well, first, it's red. We don't have too many just booming red stars in the sky. Second, it's bright. It's usually about the 10th brightest star in the sky. But the reason I particularly love it is that it's gonna explode. And this evening, I'm gonna tell you why we think this is. And then maybe I'll tell you when to be sure to be on the lookout for it. So again, thanks for having me here via Zoom. It's been a while since I've done a Zoom talk. I got very used to them during the pandemic, but fired it all up in my garage here again. So it's nice to be with you all. So Ron mentioned I do study Betelgeuse, but truth be told, if you had asked me to give a talk anytime in the previous 25 years or so, it would have looked more like this, all about stars that already have exploded, where I would show you data taken of these distant stellar explosions obtained with the largest telescopes in the world, including all those that we now have in space, high above Earth's atmosphere, including the most famous of these, the venerable Hubble Space Telescope, and its new partner in crime, the James Webb Space Telescope, just launched a bit over a year ago. And all of this work was done in an effort to reveal the secrets of these very distant, typically exploding stars that are known as supernovae. But a momentous event happened between then and now. In fact, it was just 6 years ago. And you might be able to tell what that event was. It's not a live audience, but you might be able to figure out what me and my 2 boys were doing here. I'll give you a hint. It was atop Snow King Mountain in Jackson, Wyoming. And that was right in the path of totality of the great solar eclipse of 2017, which swathed across the United States in August of that year, my very first total solar eclipse. It was magnificent. And many of you probably witnessed the solar eclipse, maybe, or saw the partial eclipse from down here in California. But if you're bummed about missing that one, you may know that you just have to mark your calendars for April 8th and then get very expensive hotel reservations along the path of totality of the April 8, 2024 total solar eclipse. Or you can see, it's not on here, but there's an annular one coming up. I think it was mentioned actually in the pre-meeting, coming up in October. But total solar eclipse, if you've never seen one, you got to do it. So make those reservations for Little Rock, Dallas, Indianapolis, Cleveland, Montreal. Pick your favorite city and make sure it has good weather on April 8th. My experience in 2017 made great memories. And what I learned is that it is much cooler to meet an astronaut than live with an astronomer. So Scott Altman was there, space shuttle crew, and my boys got to meet him, and I discovered that I had nothing on him. So it was very neat. What was actually most neat for me as an astronomer was to actually see something with my own eyes, not a huge telescope, and to share that experience with my kids and with others. And the reason being, everything I'd studied professionally as an astronomer up to that point required large telescopes to collect all the faint light from things very far away, the kind of data that you need to uncover the secrets of supernovae after the explosion. But I thought, wouldn't it be fun to actually study something where you don't need a large telescope and you can actually just point at the thing in the sky and say, right there is something I actually study. And so it was about a year after that solar eclipse, I decided to set about studying the most famous star in the sky, the Betelgeuse. And you might think it would be easy to study something that's so bright, but it turns out, as I discovered, it's not. And I have over a year and a half of my life to prove for it, because that's how long it took me and my students to reconfigure the equipment of my department's small observatory known as Mount Laguna Observatory out in the Cleveland National Forest, about an hour east of San Diego, to actually configure it so it could observe something as bright as Betelgeuse, because it's not used to doing that. And it took over a year and a half to wrestle our equipment into shape so we could actually look at this very bright star. Hard. But the timing turned out to be really propitious, because just as our equipment was coming online, which was in the beginning of the year 2020, so 3 years ago, it became clear that Betelgeuse was actually doing something funny. And if you just look at the headlines from around the turn of the decade, you can see it started making national attention here. A giant star is acting strange and astronomers are buzzing. And some of the headlines were even suggesting that something really imminent was about to happen with our favorite star. This continued into January of 2020. Okay. And by the end of January, it was getting, kind of outrageous, downright dramatic. And I even found unscrupulous peddlers selling potions to survive the big event. There you go. And the question, of course, is what was all the excitement for? And to understand the excitement of Betelgeuse possibly exploding, we just have to go back 1,000 years to July 4th of the year 1054. Here's a reenactment of what inhabitants of the earth saw then.
Imagine the night when that colossal stellar explosion burst forth.
Wow.
Stars do explode. And if one were to do this as close as Betelgeuse is, it would be simply amazing. Replacing Betelgeuse in the shoulder of Orion would be a point of light about as bright as the combined light of the quarter moon. It's about 100 times brighter than the planet Venus ever gets in our sky, which, as you probably know, gets very bright. Clearly, it would be visible during the daytime. It would cast its own shadows at night. That would get everyone's attention. But how did we get to this point? Why were astronomers getting so excited? And why are they getting excited again? In just the past 2 weeks, I gathered up a bunch of headlines here, and you can see it's all happening again. It clearly didn't explode the first time, and now we're doing it all again 3 years later. Why are we getting so excited about this? And just when will it actually happen? Well, that's what I'm going to try to tell you about this evening, but the best answers we have to these questions, and it begins by letting me just remind you of where we are in the universe. So our sun and its retinue of planets, of course, is not alone. We sit in a vast stellar system that's known as the Milky Way galaxy. It contains over 100 billion stars that are just like our sun, and they're all bound together by the force of gravity. Our sun sits out about here, far away from the center. It actually orbits the center of our galaxy, completes one orbit every 250 million years. You could call that a galactic year if you like. And you probably noticed this isn't a picture of our galaxy, it's a portrait of the Milky Way drawn by an artist based on our best guess of what the Milky Way would look like, should we ever be so lucky as to be able to send a spacecraft outside our galaxy, turn around and actually take a picture of it. We're not even close to doing that yet. Problem is, the distances in astronomy are just so vast, and they're so vast that we typically always measure distances in terms of how long it takes light to travel from one place to another. And to give you a sense of how big, how enormous our galaxy is, I always like to start really close to home and just look at the most familiar object in our sky, the moon. We actually have gone to the moon. Yes, we've been there, we've landed on it. It shines by reflecting the light of the sun towards us. And the moon is about 200,000 miles away. And it turns out that's about how far light travels in 1 second. And what this means is that when you actually see the moon, you're actually looking at light that's taken about 1 second to bounce off its surface and make it to us. So you're actually looking back in time about 1 second when you look at the moon. So you could say the moon is 200,000 miles away, or you could, if you wanted to, say it's 1 light second away and let light second be the distance that light travels in 1 second. Sun is self-luminous like all stars. It's a hot ball of gas, gives off its own light. It's about 500 times further away from us than our moon is. And if you do the math, that means it takes light about 8 minutes to reach us. So you might say the sun is 8 light minutes away from us. And one of the amazing things astronomers have learned fairly recently is that our sun is actually just like all of those other stars we see in the night sky. It's just right in our face. It's so much closer. And to get a sense of how much closer, here's a picture of the closest one of these other stars, known as Alpha Centauri. And how long does it take light from that star to reach us? It's about 4 years. So you go 8 minutes to 4 years. It means the nearest star other than the sun is 4 light years away from us. You're looking at Alpha Centauri as it was 4 years ago. You're always looking back in time. So when we return to the whole galaxy, you can see why we've never traveled outside of it to get a picture. From end to end, we estimate that the Milky Way galaxy is about 100,000 light years, tip to tip. And we sit about 30,000 light years from the galactic center. The most distant spacecraft from us that we ever launched is Voyager 1. It was launched in 1977, and it's still less than 1 light day away from us. So we're not even close to getting to the nearest star, let alone to getting outside our galaxy to take a picture like this. So I blew it there. So that's why we have to look at a portrait. But we have an amazing perch sitting in the outskirts of the Milky Way to view the rest of the universe. And when we do, what we find is that it's littered with other galaxies, literally billions of them, each containing their own retinue of up to 100 billion or so stars. Closest major one is the Andromeda galaxy. It's about 2 million light years away. And this is the closest major galaxy to us. 2 million years, you're looking in the past when you look at that galaxy. And as we look further and further away, we just see billions of galaxies. Some look like this, some look like this. Each one of these containing upwards of 100 billion stars, of which a very small fraction, about 1 out of every 400 stars that is born in our universe, will end its life by exploding. And that might not sound like a lot, but remember, there are over 100 billion stars in a typical galaxy. And so if you work out the odds at any one time, it tells you that you can expect roughly one exploding star per century per big galaxy. And since there are billions of galaxies in the observable universe, it actually works out to about one supernova per second happening somewhere in the universe that we can see. We don't discover nearly all of these, but we do catch a few thousand of them now with all the searches that are going on. Let me show you what a supernova looks like in another galaxy, not like the one in 1054 that was in our galaxy. This is a very famous galaxy. It's known as the Whirlpool Galaxy. We estimate it's about 23 million light years away, so just in our backyard, one of the closer galaxies. And this is a picture of it, taken by an amateur astronomer in early 2011. Galaxy was happily minding its own business. And I just want to make sure you're clear what you're looking at when you see this picture. There's this fuzzy, swirly thing. That's the combined light of over 100 billion stars, 23 million light years away, part of the Whirlpool Galaxy. All of these dots are stars that are right in our face. These are in the Milky Way. They have nothing to do with this galaxy. They just happen to be lined up with it. So you're looking through a screen of Milky Way stars to look at this much more distant object. These are probably tens or hundreds of light years away. This is 23 million light years away. So you have to kind of remember the different distances you're looking at. But in 2011, one of the stars in this galaxy decided to explode. And what I'm going to do is show you the picture. This was the before picture, and here is the after picture, and see if you can spot the exploding star in that galaxy. There's a new star in the second picture that was not in the first picture. And if you're having trouble seeing that, it helps if you blink the images. So here's before, and there's after. Now you see it. Before, after. And what I want to impress upon you is that this star is 23 million light years away, and it's rivaling the brightness of one that might be 50 light years away in our own galaxy. When a star explodes, it can become 10 billion times the luminosity of our sun. All right, so these are enormously bright events being so far away. So this was always the, for the last 10 years, the best picture I have had of a nice nearby supernova, a nice before and after. But it turns out that in just the last week and a half, I can show you another supernova. This one is only 21 million light years away, because just as luck would have it, in the Pinwheel Galaxy, a brand new supernova appeared about a week and a half ago. And it's bright enough that if you have a 4 or 5 inch telescope in a dark site, you can see it through the telescope. That doesn't happen very often. It's around 11th magnitude, which is really bright. This happens about once or twice a decade. You get one that's this bright. And so both of these were taken with a 4-inch telescope, actually. So the question is, of course, if we do see these things all the time, what's all the excitement about Betelgeuse? It's only 500 light years away. So we're talking millions of light years, and then suddenly we're talking 500 light years away. And what's special about Betelgeuse? We've been studying it for centuries, and it is just the kind of rare star, the 1 in 400, that we think will end its life by exploding. It's in fact called a red supergiant, red for obvious reasons, and supergiant because we run out of adjectives to describe how big stars can get. This is the biggest of the biggest stars, humongous star, both in terms of size and in terms of how much mass it has. And if you want to get a sense of how big Betelgeuse is, it behooves us to compare it to the solar system. So this is a little orrery of a top-down view of our solar system. You've got the sun, Mercury, Venus, Earth, Mars, and Jupiter way out here. And what if Betelgeuse suddenly just replaced our sun? Well, if that happened, we'd be inside the star. Betelgeuse puffs all the way out and would be skimming the orbit of Jupiter. And we know this because it's one of the very few stars, other than the sun, that we actually have resolved the disk of Betelgeuse in the sky using very complicated telescopic techniques. at only 500 light years away, and it's being so big, this is actually a picture of its surface. And I can make it so you see that there's just the picture. That is actually the surface of this red supergiant. It was taken in early of 2019 before it started misbehaving. And I'll show you some pictures after it started misbehaving. But that's the actual resolved image of Betelgeuse. So it's huge in terms of size. And in terms of how much mass it has, we think it's something like 20 times the mass our sun has. And that's a big star. Nature makes very few of these big stars. And in terms of its luminosity, the amount of light that it gives off, it's shining about 100,000 times more luminous than our sun. So it's just an enormous star. And these types of stars are rare. Only about 1 in 400 will ever get to this supergiant state at the very end of their lives. And it's a time during which we know at some point they explode. How do we know this for sure? We've seen it happen. In the last couple decades, we've now seen it happen to stars that look exactly like Betelgeuse. Not in the Milky Way, but in other galaxies. I'm going to show you proof. This was a very nearby supernova in 2008. Astronomers are very creative how we name these things. They're named alphabetically in the order that they're discovered in the year. So this was 2008 BK. It was about 13 million light years away. This is an image of it. That's the supernova. This is the host galaxy here. This was a picture taken from a ground-based telescope, but the Hubble Space Telescope then pointed at this and got a much more highly resolved image. This little box here looks like this when Hubble takes a picture of it. There's the supernova, and you can now see all these other little stars in the image. Okay, so much more clarity being above Earth's atmosphere. But it turned out that fortuitously, another image of the with high resolution, not as high resolution as the Hubble Space Telescope image, but high enough, had been taken just a few years before the star exploded. And such images at high resolution are rare. We only have them for about 24 events or so, but here it is. This is an image taken of the same part of the sky at high resolution, and you can see it's not quite as good resolution as the Hubble Space Telescope, but you can start matching the stars up. Like this blur is actually these two stars. You can see this star and this star is this one and this one. You can see these guys down here. They were taken at different wavelengths, but you can match up the stars. And when they do the alignment, what they find is that sitting right where the supernova now sits is a star that looks just like Betelgeuse, a red supergiant in the galaxy 13 million light years away. So looks just like Betelgeuse. We've seen this actually several times now. And so we know that these red supergiants explode as a supernova. And by just like Betelgeuse, I mean it has the same color, meaning it has the same photospheric temperature. It's the same brightness. It has the luminosity Betelgeuse does, 100,000 times the luminosity of the sun. And just to prove that this star actually did blow up, the same group that got this picture fortuitously waited a few years after the supernova calmed down and went away and got another picture to show that the star was gone. Because if it really blew up, it shouldn't be there anymore. And there it is. It's gone. So definitive proof that a red supergiant exploded. I did a lot of work on this kind of thing. If you want to see a boring paper I wrote, here's one. But painstakingly trying to line up archival images with current supernovae and trying to understand exactly which kinds of stars explode was something I spent a number of years doing. What we kept finding, what everyone else kept finding, is that they were red supergiants, the same kind of star as Betelgeuse. And so you could see why the prospect of studying a star before it explodes was very exciting to me. And it's just sitting there beckoning us. So we had a very good observational evidence that Betelgeuse is definitely worth watching. When is it going to happen? And why did folks get so excited about it 4 years ago? And why are they getting so excited again today? For that, we got to delve deep into the heart of the matter, literally, because we think the thing that triggers the star to explode is not at the surface. It's in the very center. It's in the core of the star. What's happening at the surface is just an indication of what might be happening in the core. So briefly, let me tell you why we think stars explode. And it begins with understanding how a star actually lives. During a star's life, consider it a big ball of gas. There's a fundamental war being waged here. It's a war between opposing forces. On one side, you've got gravity, always trying to pull the star in. If gravity had its way, it would just crush the star down to a black hole. Okay, but pushing out against that is this hot ball of gas. Yeah, gravity wants to compress it and shrink it. Okay, but while a star is living, there's a very strong force pushing out against gravity, and it's basically the force of light itself. Believe it or not, light actually exerts pressure on atoms. Okay, and in the core of the star, there's a tremendous energy generator, which makes a tremendous amount of light, which pushes out against the gas's gravity as it makes its way out of the star, finally being released from the surface. This push opposes gravity and keeps the star puffed up and in equilibrium. And it's these two forces, gravity in and pressure out, that serve as a balance during a star's life. For a normal star, the fuel for this energy generator is the simplest element and the most abundant one in the universe, hydrogen. It's the simplest because if you remember your chemistry, simplest element on the periodic table is the one that sits up here with one proton in the nucleus. And basically, when the universe began 14 some odd billion years ago, there was hydrogen, not much else. And so stars are basically big balls of hydrogen gas held together by gravity. And hydrogen just has one proton, okay? And what's happening in the core of the star is that hydrogen nuclei are so hot, okay, tens of millions of degrees hot, that occasionally two of the protons, which repel each other because they're both positively charged, slam together so hard that they overcome the mutual electric repulsion, that they get so close to each other that they actually stick together due to a nuclear force that only exerts itself over very tiny distances. And the moment they pound together and stick together to form the next element, helium, which has two protons in the nucleus, whenever that happens, a little bit of light is produced. Technically, a little mass is converted into energy, which is light, through Einstein's equation, E equals mc squared. And when you've got billions of atomic nuclei doing this every second, a lot of light gets produced. And that's the secret. In the cores of stars, light elements are being fused into heavier elements. This is called nuclear fusion. It creates the light that pushes against the envelope of the star and keeps it puffed up and in equilibrium during its life. The problem is that, like a car runs out of gas, eventually the core of the star runs out of hydrogen. It gets used up. All you've got is helium. And elements heavier than hydrogen can do the same trick. Helium can fuse into heavier elements too, but they need even higher temperatures because there's more protons in their nucleus, more electric repulsion, higher temperatures are needed to get them going fast enough to jam together. So hydrogen is one proton, helium is two, it's twice as hard. And for stars like the sun, this will happen. Eventually, helium will be the fuel source for the sun. Right now, it's hydrogen. But eventually, it will be helium. And it turns out when helium fuses, it produces carbon and oxygen, 6 and 8 protons. And then after spending billions of years, okay, literally, our sun will live about 10 billion years, 9 of which it's going to spend fusing hydrogen into helium, about 1 billion years helium into carbon and oxygen. But for 399 out of every 400 stars the universe makes, that's it. It can't fuse anymore. It simply does not get hot enough to jam together carbon and oxygen nuclei with all those protons, and the star dies. So our sun will die. It will not explode. It's going to do something neat in its death state, but is not going to be as dramatic as an explosion. The way our sun's going to die, we've seen other sun-like stars do this, is instead of exploding, they gently puff out a lot of their outer envelope into space. something known as a planetary nebula, misnamed, but that's what we still call it. And about half of the star's mass can get pushed out into interstellar space, and then the core of the star actually shrivels up and compresses under gravity with no more nuclear fusion to stop it, and it shrinks all the way down till it's about the size of the Earth. That's about 1/1 millionth its original volume. And then a new pressure support is found. It's not nuclear fusion, but it's a quantum mechanical force known as electron degeneracy pressure that stops the core from collapsing. And at this point, you get something called a white dwarf. That's the fossil that remains after 399 out of every 400 stars dies. You get a dead star known as a white dwarf. Any star that's born with less than 8 times the mass of the sun, we think, ends up as a white dwarf. We see thousands of them littering the Milky Way galaxy. Nowhere in that story is there an explosion. For that, you have to look at the 1 out of 400 stars that nature mints that's bigger than 8 times the mass of the sun. Their fates are entirely different. And the reason is they start by fusing hydrogen into helium and then helium into carbon and oxygen. But we got to make 2 points about these stars. First, when they begin fusing helium into carbon and oxygen, the temperatures are so incredibly high and the fusion occurs so intensely that in this battle between gravity trying to contract it and nuclear fire pushing out, it temporarily gets won by the nuclear fire. And that's what bloats the star way up into a supergiant. So when we see one of these red supergiants, we know it's nearing the end of its life because we know it has helium at least burning in the core. It's done with hydrogen. So when you see a supergiant star, you're witnessing a star that's nearing the end of its life. And that is the stage that Betelgeuse has to at least be in by virtue of the fact that it's swelled up. We know it at least is done with hydrogen. It's fusing helium into carbon and oxygen in its core. Once carbon and oxygen are formed, unlike the lower mass stars, these stars don't stop there. The core temperatures are so hot, I mean, over 1 billion degrees, that they're able to fuse heavier and heavier elements. They're able to jam carbon and oxygen together into neon and silicon, all the way up to the element iron, which has 26 protons in its core. And when that happens, you get a very interesting structure for the star. Basically, you have an iron core surrounded by shells of progressively lighter and lighter elements, which are the end products of all those earlier rounds of nuclear fusion until you go all the way out to the edge, and there you've got the hydrogen envelope again. But as you dig in, you get heavier and heavier and heavier elements. But it turns out the laws of quantum mechanics say iron is it. You can't get more energy out of nuclear fusion once you produce iron. It's not an exothermic reaction at that point. And so the star gets stuck without a fuel source, even for these heavyweights. And when the iron core gets massive enough, maybe about 1.5 times the mass of the sun, that's just too much gravity. And there's no more nuclear fusion happening in the core. The mass is just so great that this iron core collapses catastrophically. In less than 1 second, the core implodes. It collapses down from about the size of the Earth down to something the size of a city like my city, San Diego. And in this collapse, the protons and electrons essentially get squeezed together to form neutrons. You get a collapsing ball of neutrons. And when the ball reaches the size of a city, it stops, it halts. There's a new nuclear force that just halts the thing suddenly. The rest of the star falls in, smashes into the proto-neutron star, as it's called, and a shock wave develops that then ejects the envelope out into space, and that is the birth of a supernova. So at that point, that's when the star becomes 10 billion times the luminosity that it had during its lifetime, and shines with a brilliance that for a time is just astonishing, and then it fades gradually over time. This is the exact fate that we think awaits Betelgeuse because it awaits every red supergiant. The problem is timing this event, right? We know by virtue of the fact that it's a red supergiant that Betelgeuse is done fusing hydrogen into helium in its core, but that's about it. The problem is it can fuse helium for about another 1 million years. Okay. Everything is fast for these high mass stars. 1 million years is really fast for an astronomer, not for a human being lifetime. So we're pretty sure it's going to explode in the next million years. The question is it more advanced than that? I mean, if it's fusing carbon, then there's only at most about 2,000 years left. If it's fusing neon, we're talking a few years left. If silicon, it's just a few days till the thing's going to explode. If only we could dig into the core of Betelgeuse, but we can't. We only see the surface. And so we get very excited if we see something weird happening to the surface because we think maybe it's indicating something weird happening in the core. And that's exactly what happened to Betelgeuse 3 years ago. People have been watching Betelgeuse for thousands of years because it's so bright. And it was first noticed in the 1830s that it varied in brightness. It was not always the same brightness in the sky. And for the past 100 years or so, we've been keeping very careful track of how bright Betelgeuse appears in the sky. Let me show you what's called a light curve of Betelgeuse. It's a plot of how bright it is versus time. And I have this going back about, I think, 10 years. Yeah, about 10 years. Okay. Each of these points is a data point from often amateur astronomers, charting how bright Betelgeuse is. And these are in magnitudes, which are terrible. So I'll just say typical brightness is about here. This represents Betelgeuse being about half as bright as is typical. And you can see it goes up and down and up and down. Any idea what these gaps are? Why was no one observing Betelgeuse at the same time every year? It's behind the sun. Some of you probably knew that. In the summer months, it's out in the daytime, unfortunately, not at night. We are starting to actually get very ambitious daytime observations of Betelgeuse. You can actually see it in the daytime if you know right where to look. But historically, we didn't get those data. But you can see it goes up and down. It's a cyclic pattern. And I chopped this off right here in 2019. And here's what got everyone's attention at the end of 2019. It just fell like a rock. I mean, you could literally look up in the sky and know that Betelgeuse was wrong. It dropped from being like the 10th brightest star to like the 35th brightest star. It decreased from its normal brightness to about a third of its normal brightness. It was really dim. It just looked wrong. It just dropped like a rock. And that's what got everyone's attention. And you could just look in the sky and towards the end of 2019, and this is what it did over the next several months. This is a little video. It just kind of went really dim. And that's what led to all the headlines. Hyperbolic speculation. Okay, kept going on, even into February. And by the end of the month, the press was starting to get a bit annoyed that it hadn't exploded yet. They're talking about another supernova. It's not Betelgeuse. Don't get too excited. But there was always a problem with making such a prediction. And the problem is, of course, the trigger for the explosion is inside. It's in the core, not the surface. Just because the surface was doing something weird, getting very faint, the question was that telling us anything about the core? Probably not. And if you remember all these progenitor stars, the stars that gave rise to known supernovae, in none of those cases for which we had some historical background did these stars ever show some huge variation in brightness right before they exploded. And so the scientific evidence wasn't very good for a dimming preceding an explosion. Okay. And so theory and observation began by May, like, okay, it might not explode, okay, but you still found clickbait going all the way out into May, into May, all right? But reports of its imminent demise got completely taken down once Betelgeuse's light curve returned to normal brightness. It recovered, okay? And it's clear that what happened was just an unprecedentedly large dip, by far the largest we'd seen in the last 100 years, that bottomed out in early 2020 and then resumed its regular pattern of variability. If you want to see what's been happening since, here's the data extended through the start of this year. So it dimmed again, and then it oscillated up, down, up, down, up, down, up, down. And that was the beginning of 2023. But in the last 6 months, 5 months, this is why people are getting excited. It's now brighter than it's ever been. So everyone's getting all excited because now it's brighter than it's ever been. Okay, it's at like maximum brightness. I mean, it didn't explode when it was faintest. Maybe it'll explode when it's the brightest it's ever been. So just when will it explode? If you get past all the hyperbole, eventually what you always find in this massive articles is an article that gets it right. And it turns out in 2020, that article was one that got it right, and it was good because they interviewed me. Okay, so there you go. So they better have gotten it right. And you can see the title gets you to read it, but then the first line: any day now or night, the red supergiant is expected to explode and go supernova. Any day that is within the next 100,000 years or so. That's me talking, and that's still my answer to when is it going to explode. And it's also true that in the recent excitement, you can find articles that get it right. Okay, probably won't explode. To be absolutely truthful, if I had to hazard a guess, to be really conservative, I would say it's going to explode in the next 1,000,000 years, because that pushes it all the way back to the beginning of helium burning in the core. If you really force me to answer, I'd say probably in about 100,000 years, based on some evidence from surface, the chemical composition of the surface that suggests it's starting carbon burn. It's in the helium burning phase, but nearing the end of it. But it's pretty weak evidence that we have. So unfortunately, the best I can actually do is promise you in the next 1,000,000 years, almost promise, that it's going to explode. Maybe 100,000 years would be a good time to come back. But keep watching, because it wouldn't surprise me at all if it blew up today, which, if you think about it, really means it blew up 500 years ago. So if it blew up anytime in the last 500 years, we still don't know. The information is still traveling to us. We have no way of knowing until it arrives. But it also leaves us with a second great question. Why did it get so dim, unprecedentedly faint, and why is it getting so bright now? And believe it or not, part of the answer to the dimming question was revealed by data we took at Mount Laguna Observatory. We happened to start our observations right in the beginning of 2020. Couldn't have been better timed. And my master's student, Robert Baldocchi, wrote his thesis on this. And essentially, the data that we took revealed that the surface of the star cooled during the Great Dimming. And basically, I'm not going to train you to be a spectroscopist here, but these are the actual data, the spectra that we took. January and February was when it was in the Great Dimming, and it doesn't take a trained spectroscopist to see that the green, red, and black data are different than the blue data. The blue is when it returned back to normal brightness. And basically what you're looking at is the light of Betelgeuse dispersed with a prism and spread from blue light to red light, and looking at how bright the star is at every one of those wavelengths. And the difference in how bright the star is at these wavelengths actually is a temperature indicator, telling us that it was much cooler, believe it or not, in these epochs than it is here. If you want a really good explanation of how that works, invite Bobby to give you the talk, because it's his thesis that I'm reporting on here. But surface cooling, it turns out, can't explain the entire dimming. It can explain like half of it. And so there's another proposal to explain kind of the other half of why it got so dim. And that is that the star suffered an eruption. Don't ask why, we don't know. But it suffered an eruption that spewed out a whole bunch of material that then cooled and condensed into dust, which then blocked part of our view of the star itself. And so we actually had part of the star occulted by this dust cloud caused by it having belched it out earlier. And it's the combination of these two events that led to the Great Dimming. Okay. And then if you're asking why is it getting so bright today, essentially the best theory we have is that it's recovering from this dramatic event. The gases are sort of sloshing around, trying to reestablish an equilibrium, and it's giving rise to this unprecedentedly luminous stage. We don't think either of these events have anything to do with whether Betelgeuse will ultimately explode. But these are the kinds of questions that just make science so much fun. So bottom lines, why did it dim? Most likely a giant eruption from the surface and a cooling surface at the same time. We don't really know why this happened at that particular time. Why is it now getting so bright? We think it's recovering from that big event that happened 3 years ago. When will it explode? Well, I was saying sometime in the next million years, if I'm a betting man, next 100,000 years, it could be tomorrow. And if only to really impress upon you two things. A, that science is a living, breathing pursuit. And B, that I'm not being hyperbolic when I say it could explode tomorrow. Literally 2 hours before this talk, I was looking at the astrophysical preprint server, and look what just landed on the preprint server. This literally is posted today, June 2nd, 2023. All right, got my attention. So I was thinking about this talk, and here's the title: The Evolutionary Stage of Betelgeuse Inferred from Its Pulsation Periods. I have not read the paper. I have read the abstract, and I have read the conclusions. So let me tell you what the abstract says. Something pretty dramatic. So you might be seeing this in the news. We conclude, I should say it's a scientific article, so they bury anything exciting. So I'll extract the excitement out for you, because this is what the news will do. We conclude that Betelgeuse, this will be exciting to you based on what I just said, is in the late stage of core carbon burning. So it's a good candidate for the next galactic supernova. Go back to this slide. If you can remember all the way back there, what I said was, if it's in the late stage of carbon burning, the next several phases happen very fast. And so if it's really in the late stage of carbon burning, that means it's going to explode pretty soon, for an astronomer especially. But in order to find that statement, you have to wade through 15 pages of charts and tables and mathematical formulas to find the last sentence of the article. This is really the last sentence of the article. After carbon is exhausted in the core, a core collapse leading to a supernova explosion is expected in a few tens years. So, a bold prediction from this team that this thing could explode in the next few decades, which is really soon for an astronomer. And then if you really think about it, if that's really what they're predicting, that means it's already exploded, because it's 500 light years away, and we're just waiting for that information to get here. So definitely stay tuned. Have a look at Betelgeuse when it next reappears in the nighttime sky. And so shoot me an email if you notice that it's a billion times brighter than usual. And I'll be very thankful that you emailed me. So I'm going to stop there and let you ask any questions that you have about anything with exploding stars or Betelgeuse in particular.
Yeah, I have one. Or let's see, Richard, do you have one?
No, go ahead. Go ahead.
Okay. I was just wondering, does Betelgeuse have any known planets?
Interesting. It does not, as far as we know. That doesn't mean they're not there. It does not have, there are no exoplanets currently known to orbit Betelgeuse. But there is a fairly believed theory that Betelgeuse did once have a companion. That it may have been a binary star, and it may have eaten its companion. And the theory arises from the fact that it turns out Betelgeuse is rotating, but it's rotating way faster than a red supergiant should be rotating. And the one way you can increase the angular momentum of a star is to have it gobble something up that's orbiting around it, and it feeds angular momentum to the star. And so there is a belief, and it's more than just, you know, a minority of astronomers that hold the belief that Betelgeuse may have been a binary star system and it ate its companion. Because
Wow.
we have trouble explaining its high rotation rate otherwise.
Yeah.
So no planets, but
Hmm.
maybe it had a star companion before.
You know, talking about things around Betelgeuse, I'm just wondering about after the explosion. I know that when you had shown the previous pictures of supernovae, it looked like there was nothing left. But wouldn't there be some remnant left after supernova?
Yeah. So one of two things will be left for this kind of a supernova. If you go back to my description of what happens, the core implodes, and what's actually happening while it implodes is electrons and protons are getting squeezed together to form neutrons. And so what ultimately is collapsing in the core of one of these high mass stars is a big ball of neutrons. And it collapses down to this object called we call it a neutron star. And it's basically just a humongous atomic nucleus. It's incredibly dense, 1 billion times more dense than a white dwarf, the cinder that's left after a star like our sun dies. And so we think most of these stars leave behind what's called a neutron star. And we've discovered neutron stars. Jocelyn Bell discovered the first one in the late 1960s. And we now know of over 1,000 of these corpses of high mass stars. Some small fraction of the high mass stars leave behind a remnant that is too massive for even the it's called neutron degeneracy pressure that supports the neutron star. If it's more than about 3 times the mass of the sun, then the force that holds up the neutron star gives out, and there's no known force, and we actually think there isn't any force that could even possibly support that, and it crushes into a black hole at that point. And so what's left behind after one of these explosions is either a neutron star or a black hole. And we see really strong evidence for both of these ultimate ends from these high mass stars. Betelgeuse, astronomers argue what's going to be left. Most would say if it started at 20 solar masses, it should be a neutron star that's left behind. But there are that theory is not very well established, and there are some theorists who propose that there are mass regions that leave behind black holes. It's not just the heaviest ones. You might think it's only the ones that are 40 or more times the mass of the sun leave behind black holes, and that is what we teach our astronomy 101 students, but it's more complicated than that. Some theorists think there are these islands of mass ranges that could lead to black holes. So it wouldn't surprise me if it left behind a black hole.
Oh, I think that would be very interesting, obviously, but that leaves another question, just my final one. And do you know if when Betelgeuse explodes, if that would be detectable by LIGO?
Oh yeah, I think it would be. Yeah, I do think that would be. I don't know that I've read that, so I think I have to say I think it would be.
Yeah.
LIGO currently has been very good at detecting mergers of neutron stars, mergers of black holes, mergers of black holes with neutron stars, but has not yet detected an actual core collapse supernova, but we haven't had one this close. And so that's actually a good question. I'm going to say I think the answer is yes, but I don't know for sure because I haven't seen someone who really studies this stuff work out the details on that.
Well, it just looks to me as though there's all kinds of scientific opportunities when Betelgeuse goes, for us to learn a lot more about supernovae, I
Oh,
think.
yeah. I don't know where to begin.
Yeah.
I've spent my career trying to tease information out of supernovae that are always millions of light years away and are always points. They're just dots.
Yeah.
Can't resolve them. Betelgeuse exploding, we could resolve the expansion. And my primary area of research interest is this is kind of a side project, kind of a hobby, is actually trying to tease out the geometry of the explosion. And boy, would I love to be able to just see it.
Yeah.
Because all we've done so far is tease it out from the properties of the light coming from a point. And with Betelgeuse, my guess is it would create many more questions than answers. So that's what
I'm sure that,
that's what always happens.
I would
But
hope that it would clear up a few other points too at the same time.
yeah, one of the most exciting things really would also be we would detect the neutrinos from Betelgeuse, if you're familiar with these particles. One of the fundamental particles other than quarks and electrons is something called a neutrino, and they're produced in abundance in core collapse supernovae. And we would get a neutrino, and we have neutrino detectors all over waiting for the next galactic supernova. They've been waiting for a long time. And that would tell us an awful lot about both neutrinos and about the collapse process.
How many like Betelgeuse stars are you guys watching at the moment?
Well, every red supergiant is a candidate.
Okay.
Antares is another really good one that you can see in the sky. Those are kind of the two that are really close. That would just be spectacular if they exploded. There are some other very interesting stars. One really interesting one is known as Eta Carinae, which is, we think, about 100 times the mass of the sun. And it has been undergoing in the last couple centuries enormous eruptions, just sort of belching out enormous amounts of material and becoming very bright and then dimming. And so astronomers argue about what stage it's in its life, but it's going to explode also. but probably, it might even be sooner than Betelgeuse, unless this last paper that I haven't read is right. And so what I'll say gets me excited about this last paper, because there are a lot of papers that come out that argue about the age of Betelgeuse, where it is in its evolution. There are some very well-respected authors on the author list there that I don't think would be putting a name to something. So it got my eye right away when I saw who was on the paper. So I'll have to dig into it and see if I buy it. But they're basically arguing that, I showed you these light curves, and no one's really had a great explanation for why Betelgeuse varies the way it does. And so the thesis of their paper is that people have identified different periodicities in the light curve. There's some at relatively short periods, like 100 days. There's one at like 400 days. There's one at 2,000 days. They've identified all these different cycles. And the paper is making the claim that these are all, they're called harmonics of the fundamental radial pulsation period of the star. So it's a pretty bold claim. It's a mouthful, and they're claiming that only happens at the end of carbon burning. And so they're tying something that we see on the surface to something that's happening in the core. And it's pretty exciting if it's true. It's who would have thought? I mean, when I started investigating Betelgeuse, I kind of figured we would know everything about it. It turns out we know very little about it. People argue all about the most basic things about it. So it makes it fun.
Do we have data that we know of that explains the cycles that occur, so you can relate that back to what's happening internally?
Yeah, so that's been the challenge. The challenge has been trying to explain the periodicity of the ups and downs of the brightness. Usually stars that vary in brightness are pulsating stars. There's some very famous classes of stars that are really radially pulsating in what's called the fundamental mode. They're literally expanding and contracting and expanding and contracting. As they do, they get brighter and fainter and brighter and fainter and hotter and colder. And there's a pretty well-developed theory for those kinds of stars. Betelgeuse is kind of an odd variable. It's not one of the classically pulsating stars, and the period of its cycle is not terribly regular. You have to do what's called a Fourier analysis on this whole thing in order to pull out the dominant periods, and that's been a challenge to try to explain. A, do the periods exist? Because people argue whether they're even real. And then B, what could be causing these different periodicities? Because it's not just the down and up, it's the overall rise and fall. And then this was just unprecedented. So what the heck happened here? And that's where we've come up with the explanation that I gave you. And now it seems to have entered a new mode where it's oscillating more rapidly, and this is attempting to be explained as recovering from this event, and that it'll eventually get back to its normal fundamental mode. But it's not well understood why all this happens. And so an attempt to not only explain the pulsation periods, but also tie it to something happening in the core is pretty bold.
One of the things I noticed on this particular diagram here is, and to me, this is an indication that there is some regularity, is look at the years 2014, 15, 16, 17, all those curves end at a high point.
Uh-huh.
And
Yeah,
it's
one of the
that
periods.
would be the same time of the year, every year.
Yeah. Well, one of the dominant periods is roughly 350 days, I think.
Okay,
I think that's what you're picking up on there.
yes.
Right. Yeah. Look at that. Yeah, it always seems to end. You will notice that we seem to have data now going through the time of the year that we don't in the past. And that's because everyone got so excited by this, that this technique of literally observing Betelgeuse in the middle of the day was developed. It's not as precise as when you do it at night, but they can actually get photometry of this thing in the daytime. So they can see it after it comes out from behind the sun, but it's still up during the day. Yeah. It's kind of pretty remarkable.
Aside from the dramatic light show and the neutrinos, what other effect do they feel that the supernova would have on the Earth?
Not much. This is kind of a question for an atmospheric scientist or even a biologist to ask, could a supernova at that distance have harmful effects, for instance, on life? And the consensus seems to be, I'm no expert in that field, but it seems to be a supernova really close by could have extraordinarily deleterious effects on Earth. And it's actually proposed as a cause of some of the more major extinctions in the past, that maybe there was a supernova. Typically it has to be within 50 to 100 light years to damage our atmosphere to the extent that it could be harmful to life that's inhabiting the Earth at that time. 500 light years seems safe enough away. It's like the perfect distance. It's close enough that we get a bird's eye view of it, but it's far enough away we don't have to worry about being harmed by the explosion.
No aluminum hats necessary.
No, and you don't need to drink any potions to protect yourself from Betelgeuse's evil rays. So no, I would unabashedly love it to explode. Yeah, here's the Betelgeuse proof.
You're all ready with your marketing campaign.
I'll take a case.
There you go.
You don't know when it's going to explode. So every day.
Yeah, every day.
Every day. So yeah, I mean, that's kind of the thing that hit me next after I saw the title was, well, gosh, if they're right, it already has exploded.
Yeah.
Oh,
We're just waiting for the light to get here.
Sure.
It's annoying and frustrating. We have no way to find out until the light arrives. There's no known way to beat the speed of light in terms of getting information from one place to another. So even if we had a friend right at Betelgeuse, the moment they said, "Hey, it just exploded," we would get that message at exactly the time we see the light from the explosion. 'Cause you can't.
You ought to send your crew
Good job.
to Bud Light. Maybe they could help with their sales.
Yeah. Okay. They need the help.
They need the help.
I just have one question. Historically, some people have recorded, in ancient times, I should say,
Yeah.
not modern times. Do we know where these supernovas actually exploded, or do we think they were supernovas?
Absolutely. Probably the most famous one and the most accessible evidence. If you're looking for evidence, I can tell you where to go. That supernova that Carl Sagan was dramatizing there in 1054, that was observed all around the world in 1054 AD. And the closest inhabitants to us here were the Anasazi Native Americans who lived in New Mexico in the northwest corner. And there's now a national park there. It's called Chaco Canyon. And
Yeah, I've been there. Yeah.
yeah, if you go there and know where to go, you can find a lonely ledge that is now about 30 feet off the ground. I think it was much lower to the floor 1,000 years ago. And under it is a pictograph of a quarter moon, a blazing object, and a hand. And it's been dated to the 11th century AD. And we actually know exactly when that star exploded because Chinese court astrologers noted the date in their journals. And it corresponds to the modern day July 4th, 1054. It's a great day for a stellar explosion. What didn't mean anything back then, but for Americans today, July 4th would have, it'd be great to have a star explode on that day. And so we know exactly when it happened. And we find it notated in various ways all around the globe. So that was one in 1054. Then the next really well documented stellar explosion it's known as Tycho's supernova, and it was in the 1570s. And Tycho Brahe was a famous observational astronomer, the last great naked eye astronomer. And he observed that supernova. And then his disciple, Johannes Kepler, in 1605, discovered what we today call Kepler's supernova. These were all naked eye supernovae. And then I always feel like nature took note of the fact that we invented the telescope in 1609 and said, great, you've invented the telescope. Now you're going to need it to see every exploding star for the next 500 years. The only exception to this was in 1987 when a star exploded in the Large Magellanic Cloud, which is not the Milky Way, but it is only 150,000 light years away. And so that's the closest supernova we've had in modern times. We're still studying that one. So yeah, we have historical supernova going back over 1,000 years.
Thank you.
I have two questions. One, does the change in the light curve after the big event in 2019, 2020, does that argue against the idea that dust is what caused the dimming? And the second question is, will optical interferometry be an important tool to study Betelgeuse when it explodes, if it explodes soon?
Okay, let me tackle your first question. Your first question is a controversial one. And your question is a very good one, I think. And it has to do with the dust hypothesis. And what you're saying is kind of the way it dimmed and brightened. Is that really consistent with dust? I'll just say that is a controversial question. I'm being recorded, so I won't give you my personal opinion. I'll just say that is a controversial, it's a very astute question. And I'll just say that other than saying dust could cause occultation, I don't know of a model that perfectly predicts this kind of down and up, this smooth down and up as being due to any particular kind of dust blob. Yes, dust does dim. But changes in temperature also dim. And the question is whether you need both. And right now, the consensus is kind of centered around both things happening. The surface of Betelgeuse is very different than the sun in the sense that, the sun has sunspots, but sunspots are dark patches on the sun, and they're very small compared to the size of the sun. The atmospheres of these supergiants, the convective cells are huge. And so you could actually have a star spot on Betelgeuse that covers like a quarter of the surface. And so the theory that the temperature went down is basically a theory that there was a star spot that was just abnormally big that covered a large patch of the star for a time. And so that theory versus, dust occulting the thing. It is clear Betelgeuse had some kind of dramatic event at the end of 2019. They're not just making that up. There's data that shows it had a dramatic, expulsion of material prior to the Great Dimming. And so it's not unreasonable to connect the dots and say maybe that material condensed into dust, which then occulted part of the star. So it's not an untenable theory. But your specific question about whether it perfectly predicts the down and up, I haven't seen any model that goes into that level of detail. And then you had a second question, and I can't remember it.
Could optical interferometry be used to observe Betelgeuse if it were to explode sometime soon?
The answer is yes, and it would have to be actually, because even at 500 light years away, a human being looking at it would still just see a dot. You would not see an expanding ring in the sky. You still would need quite sophisticated astronomical observing techniques to resolve the expanding fireball at early times, especially. So things like optical interferometry, adaptive optics, if you've heard of that, from the ground, and space telescopes would be needed to approach the resolution needed to actually resolve the expanding atmosphere of the supernova. It would not be a dramatic ball expanding in the sky. It would just be like the picture I showed you. This is actually an accurate picture, which is why I liked it. It would really, if you want to know what it would look like, it would really look like that. It would just be a very bright dot replacing Betelgeuse to the human eye. And they even got the diffraction spikes as though you looked at it through on a CCD chip, but it would not be a big ball. It would just be a very bright dot.
Okay, thank you.
Well, thank you. That was really interesting.
Yeah, that's great.
Well,
And
thanks for
very
having
timely.
me. Yeah,
Awesome.
it turned out to be more timely than I envisioned when I was at. It just got better and better.
Yeah. Great. It sounds like we should have you back again.
Keep your eyes out, literally.
Yeah, you need to come back every month.
Watch
Yeah.
give you the latest updates that have
That's
appeared in
right.
the press and in the journals. Yeah.
Yeah, you need to come back and tell us what the latest paper was all about.
Yeah, that's right. I have to read it now to actually dig in and see if I believe it.
Well, maybe we should get together with the Betelgeuse alcohol, and then we could discuss it more thoroughly.
That's clearly what we need.
I'm all for that. Cheers.
Thank you, Douglas. Really, that was really.
Yeah, that was great.
It really
Thank-
was.
Thanks very
Right.
much. And let me
So-
also just tip my hat to you. Amateur astronomers just do so much good public outreach and good work. And I heard in your meeting how you're, doing work with young people and stuff, and it's so necessary. So thanks for having an astronomy club and engaging the community the way you do.
We'll see what we can do to ramp down some of the hyperbolic headlines.
Yeah, right. You always have to be the buzzkill.
Somebody's got to do it. It may as well be us.
Oh, I think we ought to ramp it up.
So where would this article be if we went to look on the internet?
Yes, if you wanted to look at it, let's see, I can show you. Let me see if I'll show you on the internet, and then you can want to actually tackle this yourself. So in astronomy, the way it works is, so I should say this article is not yet published, which means it's not been peer reviewed, which means, some expert hasn't read it and declared that it's valid. But what's in the last 20 years, what astronomers typically do is, depends how they want to do this, but they can post the article even before it's published to what's called the archive.
No.
And this is the website here. Okay. And if you go to that website, it's just arxiv.org. If you go there and you click on new, these are all the ones that were just released today. And somewhere in here is that there's usually about 60 or 70 articles every day. So I don't read them all, but when I see Betelgeuse in the title, I read it. Here it is. Okay, I just did a search. There's a 28th article today, and there it is. And then you just click on PDF, and in no time you get the PDF of the artical.
Get the whole
okay.
article.
Yeah. And so there it is. And so, I did quickly go through it and just sort of see, you'll be bored or you'll be intrigued, but it's a lot of scientific data and a lot of modeling. So these are theorists. This is a group of individuals who does a lot. You want to remember your div, grad, and curl if you took advanced calculus. There you go. So you wouldn't think studying Betelgeuse would require all this, but it does. So yeah, this appendix kind of overwhelmed me. So I thought, you don't have to understand this to get the gist of the article. But I was to say there's a lot of math and science here. And this article is written by a group of theorists and who study stellar pulsation and stellar evolution. And so it's a good group. So it's worth considering. But we'll see. Yeah, they submitted it to a journal. It's not accepted yet. But they clearly wanted to get out in front and capture the current excitement. They were probably working on this, and then the excitement with Betelgeuse just got them to get it out sooner. So you can see the periods. These are what I was telling you. They claim there are periods of 2,200 days. 420 is one that's close to a year. 230 and 185. People argue about how real these periods are.
Yeah,
I'll have to see.
but wouldn't it be something if this was published the day of the explosion?
Yeah.